one of the most celebrated symbols of all times. For sure the most celebrated symbol in our class. And that would be the integral symbol. This long little funky curve like this. It feels so good to write. Look at that. Look at that. It feels good to write it. So beautiful. And what we want to do is we want to introduce a couple things. We want to explain what it means. And we want to explain about 4 or 5 famous properties that go along with it. That's all. It's a very, very modest day today. So let me explain what it means. Quite simply, what it means is S. This is a long version of the letter S, which is supposed to represent sum. Now, a long time before that, the way people used to write sums, well, you know, at least around our culture, we get a lot of this stuff from the Greeks. The Greeks would use their version of S, which is sigma. This is their version of S, and so they never got to finish the job of cutting things up into infinite many pieces, so they got stuck in that world right there, in the sigma world. In the late 1600s, 17th century stuff, Newton and Leibniz, they did it continuously. They've managed how to do it, and they went ahead and they changed the symbol. They updated it, kind of like when iTunes changed their icon. Same thing. Newton and Leibniz came along and they changed the icon for sum. It all means this is sigma. Their version of S. This is another special version of S for calculus, and it's supposed to mean S or sum. That's really quite simply what it means. There's a lot more to it. So let me give you just enough to appreciate it, and not too much to turn it into something unpleasant. Just enough to see the beauty and the power of the sigma, of the integral. Okay, that's all I want to do today. It's an art, by the way, to do it just enough. I don't want to sound like 100 lawyers prepare this lecture where everything is absolutely rigorous. That wouldn't be fun. The ideas are really nice, and that's what I want to get to. So anyways, so what we did last time is we had this idea of finding the sums, and we went from some point, say from 2, say we went from 2 to 8. So from 2 to 8, and we would cut it up into infinite many little pieces. We would cut up into p pieces, and that would give us a bunch of little areas. We call the little areas AK. We add them all up. The AP was the sum of all the little ones, all the little rectangles, and each one of them. And then we take the limit as p goes to infinity. That was huge. That turned it into the exact area under the curve. Of course, each of these little areas is height times base. And the height we found by taking some value, like say xk, and you plug it into the function. And that's how you get fxk. It's the height of the little rectangle. Of course, the width is the delta x. And delta x for our case was the length of the interval. If this was 8 and this was 2, it would be 8 minus 2. That would be the whole thing. But then you divide it into p pieces. So each of them was 8 minus 2 divided by p. Whatever, that's what we did last time. This was called the Riemann sum. This is a special case of a Riemann sum. A Riemann sum limit. It doesn't always exist, by the way. We've seen a lot of limits. A lot of them don't exist. But if it does, then we can find the area under the curve. And we call that the Riemann sum. By the way, Riemann was a hotshot, one of the big players in the history of calculus. You know, when it was first invented, in the late 1600s, it was all based on a lot of intuition, and there were some serious critics who pointed out that these people are crazy. Newton and Leibniz. Now, can you imagine calling Leibniz and Newton crazy? Those are people with some of the highest IQ in the human spectrum. And one of the more serious critics was a philosopher named Berkeley. He said, "Hey, you guys are crazy. You guys have little quantities there that are close to 0. Sometimes they're 0, but they're not really 0 because you're adding them all up. Make up your mind. Where are they, ghosts, or what are they?" And so the criticism stood as reasonable criticism. And so for a couple hundred years, calculus was just done on intuition. It wasn't really rigorous. It took huge people, big players, to make it all tight and right. Of course, one of them was Riemann. Another one was Cauchy. If you guys want, you guys can look that up. These are big players. They fixed some of the problems with Newton and Leibniz approach. And so that's why this is called a Riemann sum. And what does that have to do with today's lecture? Well, it has everything to do with it. That's the Riemann sum gets changed, as I implied at the beginning, for the integral sign. And instead of doing this, doing where the Greeks left off with the sigma stuff, we replace it with elongated s integral. And we read this, the integral from 2 to 8, from 2 to 8, of all the little f of x's. And so you just pretend you have a small little tiny x here. It's not even xk, it's so infinitely small that it wouldn't matter which x you pick in there. And you would plug it into the function. So f of x would give you the height. That's this one. This would be the height of the function, and this would be the base. Sorry, the height of the rectangle. Infinitely small rectangle, and this would be the base. That's your taking the place of your delta x. And so this is meant to say, hey, I'm adding up all these little rectangles right here. Add them all up, the little areas that are, each one is, to get the height for each one, I take the x value and I plug it into the function f, and I multiply times the width, which is dx, and then I add them all up. This symbol right here means you add them all up, starting from x equals 2 and all the way to x equals 8. And there you go. That's the integral notation. It's a little tiny piece of it. Why don't I give you the entire story? Because I don't think it's the right thing to do. A lot of books will do it, and in fact what that does is it makes this significantly more complicated, but it doesn't add in well, how to explain it. I don't know if I should. It considers a different case. We took the optimal case when the function is nice and continuous and all that. The more general case, if you're consulting other books, it won't look like this. It'll look something like the summation of f of ck delta xk all over a set of all partitions, and you take the limit as the absolute value of the partition goes to 0. And this is a special case of that, but this is more general, and it would cover functions that maybe are not continuous. Maybe they have holes in them. Maybe they look weird like this, and the Riemann sum still works there. And this is making a statement about more general cases than the ones we did. That's all I should say, probably. For our case, under optimal conditions, this will do it. So this is the integral from 0 to 6 of f of x dx, and I'm told what the function is. The function is x over 2, so I could also write this as the integral from 0 to 6 of x over 2 times d of x. So I'm going from 0 to 6, and I'm adding up all the little tiny areas like this, that the width is dx and the height is f of x. And so if I would have infinite many of these that are infinitely small and add them all up, well, lucky for us, this is a famous shape. It's a type of shape that you could have done in preschool. This is a triangle. So therefore, the total area, which is equal to this is equal to the area, which is equal to the limit as p goes to infinity of the sum, blah, 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 the Riemann limit. Forget that. The integral notation is clean. It's a lot cleaner. The area would be, because this is a famous shape, I can figure it out. It's base times height divided by 2 for the triangle. So let me see. The base is from 0 to 6. That's 6. The height would be whatever the it is. If I plug in 6 into the function, 6 divided by 2 is 3. And I divide it by 2. And that would give me that the area is equal to 9. So there we go. We find our first integral here from 0 to 6. X over 2 dx is equal to 9. Yippee-ki-yay. Told you. See why they pay me? That was too easy because it was a triangle. Too easy. Want to try something harder? How about an upside down triangle? What if you went from 0 to 6? From 0 to 6, and the function in this case was the negative of the other one. F of x is equal to negative x over 2, so therefore this is the integral from 0 to 6 of negative x over 2 dx. Well, think about it. This is equal to the limit as p goes to infinity of the summation as k goes from 1 to p of f of what was it, 8 minus, or 6 minus 0, so it'll be 6 over p times k times the width, which would be 6 over p, blah 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 blah. Anyways, when you, this is the little, all the little areas ak. If you plug things in here, if I plug in 1 or 2 or 3, I plug them into here, I'm going to get negative values. So each of these negative values can come through the limit. As long as this limit exists and it's finite, constants can come through the limit. And what you're going to get is equal to negative, each one of these will be negative, negative, negative. So the negative will carry out throughout the rest of the problem, giving you a negative area, quote unquote. And so it'll be base times height divided by 2. Wait, but the height was not that, right? Height was 3. Base times height divided by 2. So that will give you negative 9. And I thought this was a really, really important example to do because, look, the area, if it's on top, it gives you positive 9. If it's on the bottom, it gives you negative 9. And so these integrals not only calculate area, but they do more than just area, quote unquote. They do a signed area, meaning that on the top is positive, on the bottom is negative. Here, this example will further illustrate that. Suppose you wanted to find the integral from 0 to 2 pi for sine x. That means you're finding all these little rectangles, all of them. There's many, 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 many here. And whenever you're done, every one of these little rectangles that you find, there's one over here that has a negative f value. So whatever area this is, it will cancel out with this one. And so whatever area this is, suppose this is 5 or 3 or whatever, this will be negative 5. And by the symmetry, this is easy to compute. There you go. The total integral is equal to 0 using the symmetry. Huh? Nice, huh? You can even switch it up around a little bit. If you went from negative pi to pi, same thing. This one's positive, this one's negative, that's going to be 0. Told you. These are just some basic properties for the integral. Here's an interesting one. What would happen if you take the integral from 6 to 6 of f of x dx? What in the world does that mean? Well, that means you're going to find the area starting here at 6 and stopping at 6. Well, from 6 to 6, well, that's not very much area, is it? And so exactly what you might think happens. That area would be equal to 0. Okay? Those are some of the famous properties here. It's also nice to note that you already know a lot of these properties because you know, a couple of sections ago we studied the sigma and we studied sigma properties. These were sums. They were discrete sums. They would go like 1, 2, 3. You plug these things, and these are continuous sums. So you go 1, and everything continues up to 2. Everything continues up to 3. But they're still sums. And so all the properties that you had over here have analogous versions of properties over here. Let me explain what I mean by that. Okay. Okay, do you guys remember the famous properties, right? This one was that you could split the sum into pieces. This one was that you could pull out constants. This one was that you could break things apart. This one was that you can shift the index. Every one of these has an analogous property if you just exchange your sigmas for integrals. Okay? Let me take this one for example. Okay? I think this will help. I don't want to do all of them because then this video will be like 10 hours long. But I want to do one of them. The basic property or the basic principle is that you can subtract and add pieces of the integral together. Let me explain. Before let's recall, if you had the sum of all the a_n's from 1 to 100, that would be a1 plus a2 plus a3 all the way up to a100, right? Here's an interesting way to do it. You could go a1 plus a2 all the way to say a25. And then start off at wherever you left off, a26, and then go all the way to a100. What that means is that you could split this sum into the sum of all the a_n's going from 1 to 25 plus the sum of all the a_n's going from 26 to 100. It's common sense, right? You can do exactly the same thing with integrals. Exactly the same property. By the way, we use this to shift the index also because a lot of the formulas started off with 1, so we would move things around, etc. But let's try to see how that would look like with in case of integrals. So suppose you consider the area from, say, from 0 to 7. So this would be, the total area from 0 to 7 would be the integral from 0 to 7 of f of x dx. And say, hey, what if I want to split that up into two pieces? I take an intermediate point here, say 5. And I say, hey, this is the same thing as going from 0 to 5 f of x dx plus the integral from 5 to 7 f of x dx. But this is one's a little different. These have to match exactly the same because they catch everything in between. So while the other one, there's no integers between 25 and 6, there's nothing in between. But this one deals with more than just integers. This one deals with fractions and everything. So if I start off at 6, I'll leave this whole thing blank. Imagine if I start off from 6 and I find this area and I found that area. Well, I skip this area, so I don't want to do that. I want to pick up exactly where I left off and make sure there's nothing left in between. So this is a famous property. It just basically says that integrals, you can add and subtract pieces together the way you would expect. Of course, so long as you have favorable conditions. Each one of these limits exists and is finite and blah blah blah. Okay. So this would be the property from, say you wanted to go from 2 to 8 again. You could stop anywhere you want. 5, go from 2 to 5, and then 5 to 8. I even put something interesting on the homework, I think, or on one of the self quizzes. I said, hey, could you do that even if the 5 was outside? Could you go, okay, the integral from 2 to 8 of f of x dx is equal to, get a little crazier, from 2 to 10 plus from 10 to 8 of f of x dx of f of x dx. That's a little interesting here. The answer is that you can do that. The actual number, the intermediate, doesn't even have to be in between. And it's really, really fun exercise to try to think about that. You don't need much. You just need to be able to add pieces together and subtract them and whatnot. And all the hints are there in the homework. Let's see. You could do it for sine. If you wanted to go from 0 to pi, hey, you could stop anywhere in the middle. So this would be the integral from 0 to pi over 4, for example, of sine x dx plus the integral from pi over 4 to pi sine x dx. It's easy. Intermediate. You could even get a little creative here and say, hey, what if I wanted to find this area right here? So this is y is equal to 20, and I just want that area. Could you use integrals to express that? And I'm telling you, the principle is quite easy. All you do is add and subtract pieces the way you would, just using common sense. Say we're going from 0 to 6. Could you express this area using common sense? Let me just give you some ideas on how you might be able to do that. You could say, hey, this is equal to this area. I'll just take everything, man, everything. From 0 to 6, 0 to 6, I'll take everything, everything. But then I will subtract stuff that I added that was too much. Stuff that I really wanted, just this area, right? So I don't want, for example, I don't want this area right here. No, I don't want that. So I would take that and then I would subtract this area. So I find the whole square, the whole rectangle, and I subtract the bottom piece. Then I will have, in effect, the area that I wanted. Now, how do you write that in integrals? Well, that would be, let me think, this would be the integral of, what would it say, this was 20? The integral of 20 from 20 dx from 0 to 6 minus the integral of f of x from 0 to 6 dx. And so the whole thing, I can conclude, this guy is equal to the integral from 0 to 20. No. The integral from 0 to 6 of 20 dx minus the integral from 0 to 6 f of x dx. There you go. The principle is really easy. The principle is that you can add and subtract pieces to make different pieces for integrals, okay? That's the principle. This is sort of a nice way of showing it. Anyway, so that's another way of looking at the principle. If you go from A to C, same thing as going from A to B, B to C. Showing that you can add pieces together or break them up. Let's do another property real quickly. This is called the switch. I like to call it the switch. And it considers what happens if you go backwards. All this time we've gone from 2 to 8. We've never gone backwards from 8 to 2. So what in the world would happen if you did that? Well, let's think. To do that, I could play this game here. I could go say, hey, you know what? From 2 to 2 of f of x dx is equal to 0, right? But from 2 to 2, if this principle is correct, from 2 to 2, if this principle is correct, I can stick some other value. Doesn't have to be in between. Any other value and going to the intermediate value, and then from the intermediate value back to the top of the value. Right? So if I use that property, then I could say, hey, this is the same thing as going from 2 to 8 of f of x dx plus integral from 8 to 2 of f of x dx, and that's still equal to 0. All I did is change the left side. Instead of going from 2 to 2, I went from 2 to intermediate, from the intermediate back to 2. If that other property is correct, then this should be correct. But wait, there's more. If this is equal to 0, that means I can swing this over to the other side and conclude that. So I can conclude that the integral from 8 to 2 f of x dx, that's my switched one, is equal to negative the integral from 2 to 8 of f of x dx. Meaning that switching the limits has the effect of just changing the sign. Switching the limits, if this one was equal to 8, then when you switch it, you get negative 8. That's the switch property. I can summarize it like this. If you have the integral from a to b of f of x dx, and I switch it, instead of going from a to b, I go from b back to a. What that does is put a negative there. That's the switch. Okay. Some more analogies. You guys want more? Maybe I'll do one more analogy. Every one of these things that we learned before for sums of famous properties has an analogous version when you do the sigmas. So maybe for fun, I think I want to try that one. Of course, that one was equal to p times p plus 1 over 2. We all know that. And of course, we made a picture of it. You'd say, I'll write it in symbols, better numbers. 1 plus 2 plus 3 plus 4, all the way till you get to p. And the picture for it is one little block, and then two little blocks, and then three little blocks, etc., etc., etc. So what that turns out to be is this area of this shape, more or less like this. What we want to do is find an analogy of that for integrals. What does that mean? Well, that means you've got a function here, f of x is just equal to x, and you've got a width here, dx, and you're finding all the little areas. Every one of these is a little area, dx, and the height here is f of x, which is equal to x. And you're adding them all up. You're adding them all up, starting at 0 and stopping at p. And so that's the analogy. This is the discrete version. They call it discrete because it goes through the integers. Would be the continuous version, continuously finding all the little heights and all the little rectangles. And we can do it. I mean, if we can't do it, maybe at least you could do is just substitute some value here. See if you could do it for. Maybe you can't do it for p, but maybe you can do it for 6. And so that would be the area under this triangle from 0 to 6. And the f of x is equal to x. So if I plug in 6 in there, I get that the height is equal to 6. So the area is base times height over 2 because it's a triangle. And so you get 18. Oh, that was too easy. fact, you don't want to say 18. You want to say 6 times 6 over 2, because you don't want to hide the pattern here. Let's look at the pattern. From 0 to 13, x dx. Well, that would be the triangle from 0 to 13. At 13, you would plug in 13, so it's just 13 times 13 over 2. Base times height divided by 2. Check. All right, so if you had to guess, what is the pattern here? From 0 to p, what would the area be? This area would be equal to p times p divided by 2. And there you go. That's the analogy. Look at the two. This one, summation of all the n's, as n runs from 1 to p. This one is p times p plus 1 over 2. This other one, summation of all the x's dx's, as x goes from 0 to p, is equal to p times p divided by 2. Look at that. P plus 1 over 2, p times p divided by 2. They're almost the same. This is almost p squared on the top, and this is p squared on the top. They are so closely related. This one is just taking continuous, all the little tiny, super tiny rectangles. Yeah, I can see why Berkeley was criticizing this. They're sometimes 0 and they're not 0. Hey, 1 point for Berkeley. While this one doesn't do the continuous one, this one just does the jagged ones, the ones that are just like a step. So you would expect maybe they're not the same, they're slightly different, but you would expect them to be very similar, which they are in case. And so you're now cordially invited to try and see if you can find analogous things for all the other properties, the famous ones in here. They all have some analogous property, and it might be fun for you to try that. But I think that will do it for me. I think I'll just write a summary of the famous properties here. We defined a new way of writing this special case of the Riemann sum, and we said, hey, we can write it with integrals. And then we studied a lot of the properties. We did the switch. If you switch these two, you change the sign. We did the crazy area from A to A, where you stop and start at A. That's equal to 0. We did the sum of the pieces. If you go from A to C, you can go to any intermediate value. Check. And we talked just briefly about a more general integral, Riemann integral, for functions that may or may not be continuous, so long as they're bounded and they meet other requirements. This limit will exist under some conditions, but you have to extend this definition. You have to change it slightly, which I don't want to do too much right now. I don't think it's prudent to do it at this moment. Anyways, I think that will do it for me.